Okay, the next few topics we're going to focus around internal combustion engines and how we analyze the performance of that. So when we're talking about an internal combustion engine, we're talking about a piston cylinder where, this is reciprocating. I get rotation from it, pulling in air and fuel, spark plug, blowing it up, that sort of thing. Okay, and we're going to talk mainly about, here we're going to talk generally about internal combustion engines. We're going to talk about four-stroke, then we'll talk about how we actually analyze specific cycles after that. So generally we're talking about a four-stroke engine. So the first stroke is an intake where basically the piston pulls down, pulling in fuel and air. Okay, so we pull that in. Now I'm down here at the what we call the bottom dead center position. Okay, then the valves up here close, the valves being where the fuel and the air are coming in. Those close, and the piston moves up to the top dead center position, compressing that air and fuel, increasing the pressure and the temperature. Once it gets up to that top dead center, the spark plug goes off, right, causing an explosion, which, combustion occurs, and rapid expansion occurs. That's called the power stroke. It pushes that piston back down. Okay, once it gets down to the bottom dead center, the valves open back up and the gases are purged out, right? And then the fresh intake valves open and we pull it back in and the process starts over. So that's the general cycle of an IC engine. Okay, now a couple of terms that we have. One is the compression ratio, which is essentially the ratio of the volumes. Okay, basically the maximum volume divided by the minimum volume, the bottom dead center and the top dead center. Okay, so that volume ratio is an important aspect that we will use in the analysis. That's called the compression ratio. A measure of performance we have is the mean effective pressure. And this is basically the theoretical constant pressure that would produce the same amount of work, right? So we take that pressure times the change in volume, that gives us our work. That's our mean effective pressure. Okay, and that's just another way to describe the performance in terms of pressure versus, versus the work or what have you. Okay, now we're going to use an air standard analysis. This is the preferred method. We're also going to talk about another one which I don't prefer quite as much. We'll talk about why as we talk about that. Now, this is a very kind of first order approximation of what's going on. This process is really complicated, but we're trying to condense it down so we can actually do some analysis and learn some things about each different cycle, okay? So these are the assumptions we're making in an air standard analysis. First of all, we're going to assume that there's a fixed amount of air. We're going to treat this as a closed ideal gas system, okay? So there's no real exhaust or intake, right? There's a fixed amount of mass in there that we're going over, okay? Combustion, very complicated process. We're just going to assume that's some sort of external heat transfer. So we're just going to say, hey, it's a Q in from combustion, as opposed, that model of basically the air exploding is a pretty complicated model. We're just going to say, hey, there's some Q in or Q out, or well, I guess Q in for the combustion. Okay, and again, we're assuming there's no intake or exhaust. It's a fixed amount of air as we're going to model it. Okay, so we don't have that intake exhaust process. Again, we're simplifying it so we can do some analysis and get some idea of how things are performing. Now, a further simplification, and a simplification I am not a big fan of, is the cold air standard, where we assume constant specific heat. And we've talked many times about why we don't really want to, specific heat is not constant, especially over these large ranges of temperatures that we're going to get in IC engines, going from, room temperature up to thousands of degrees. Not exactly a range where the specific heat is going to be constant. However, we can learn some even more crude models, understanding of what's going on with that assumption. So we'll talk a little bit about it, but generally I'm going to talk about the air standard analysis. Now, the first type of IC engine we're going to talk about is the Otto cycle. And really the difference between these different cycles is how heat addition occurs. And with the Otto cycle, we're going to make the assumption that heat occurs instantaneously at the top dead center position. So there's this constant volume heat addition. Okay, so our processes basically we flip-flop between isentropic and constant volume process. So we've got the isentropic compression, then we have again that constant volume heat addition where I just assuming some sort of external Q in, and that occurs without, instantaneously no change in volume. After that heat addition occurs, then I have an isentropic expansion. Again, that's my power stroke. That's what I'm getting out. Okay, when it gets down to the bottom, we're just going to assume there's a constant volume heat rejection. So again, rather than doing the exhaust and intake, we're just going to say, hey, we get rid of the Q, and then I go back into the compression process and repeat the cycle. Okay, so again, isentropic, constant volume, back and forth. Okay, so with these constant volume processes, there's no work being done. With the isentropic processes, there's no heat transfer being done. So basically, it's just delta U for each process to find the work or the heat, using, again, that air standard analysis, which is the preferred method. Therefore, the thermal efficiency is the work of the cycle over Q in. So that's, 2 to 3 minus 4 to 1. Okay, all over the Q in that I have there as well. Okay. For those isentropic processes, again, we've got that compression ratio, which is the volume ratio. So we're going to use those isentropic relative volume ratio values in table A22, I believe it is. Right? We use those relative volumes for the isentropic processes. So knowing the compression ratio, and knowing it's an isentropic process, I can figure out going from state 1 to 2 or 3 to 4 or what have you. Okay, because I know those for an isentropic process. Now, again, cold air standard analysis, I don't want to dwell too much on this because I don't prefer it. But basically what you're looking for here, rather than U values, is you're looking for just the temperatures. Once I have the temperatures, I can use specific heats to figure things out. Okay, K is my specific heat ratio. R, again, is my compression ratio, so you can see the relationship between the temperatures and the K values. And in fact, I can relate my efficiency directly to that specific heat ratio and that compression ratio. And from this, we can learn that in general, the higher that compression ratio, the higher my efficiency is going to be. So the larger that volume change, the better my performance is going to be. Okay, so that's an Otto cycle. Again, I've got constant volume heat addition. That's what separates this from the ones we'll talk about in the future. And again, air standard analysis, where I'm finding U values, is the preferred way of doing that.